Let's compute the map, the maximum a posteriori estimate, for the mean of a univariate Gaussian. Univariate Gaussian. So this should be a simple calculation. I haven't worked it out ahead of time, but we'll figure it out together. So before, in another video, we computed the MLE for the mean of a univariate Gaussian, and now we'll do the map. So let's set things up for computing a map. So we need some data. We assume we're given some data, x1 to xn, and here these xi's are just in R. These are points. These are going to be points that are coming from a univariate Gaussian. And we will suppose, so the first step was to assume some data. The second step was to assume a joint distribution on a parameter theta and the data. So we're going to define a joint distribution, and we will suppose that theta is a random variable, and theta we're going to interpret as the mean of the Gaussian. And theta, so theta is a random variable, and it's distributed according to some distribution. Actually, so let's choose a particular distribution. Let's choose it to be normal with mean, let's say mu, and variance 1. Just to keep things simple. And also, so suppose that, and we have some random variables, x1 through xn, which we will assume are conditionally independent given theta, and distributed according to, so let's say, and condition on theta they're distributed according to p of, well, let's just write out what that is. So we assume some conditional distribution, which is normal with mean theta and variance sigma squared. So sigma squared we're assuming is known. You could assume that it's, we want to estimate this too, but we'll keep things simple for now. So all this means, right, all this stuff about this conditional independence, all this means is that the probability that x1 equals little x1, x2 equals little x2, up to xn equals little xn, given theta, factors according to this, and each of these, so that's the conditional independence part, and then this part says that each of these conditional distributions is just a normal with mean theta, variance sigma squared, i.e. this. So now, what is the map? We need to compute the map. Well, the map, or rather I should say a map estimate for theta, to be precise, since we don't necessarily know that it's unique, is a maximizer over thetas of the posterior distribution on theta given the data. And now this thing, so we can rewrite this. Let's rewrite this. We can rewrite this by Bayes' rule, if you remember your Bayes' rule from probability, as the probability of the data given theta times the probability of theta divided by the probability of the data. And the argmax over thetas, because P of D, the probability of the data, does not depend on theta, then the argmax, a theta which maximizes just the numerator, also maximizes the whole thing. So we can rewrite this argmax as the argmax of just the numerator part here. And going further, using our trick of taking the log, since this is an exponential, Gaussians are part of the exponential family, taking the logs is probably a good idea. So we can take the log, and that is also equal to this argmax. Log of the product is the sum of the logs. And we have this. Log of the probability of the data given theta plus the log of the probability of theta. And we'll do the usual calculus thing, differentiate with respect to theta, and set that equal to 0 to try to maximize this guy. So let's try that. So let's differentiate. So we'll say 0 equals the derivative with respect to theta. Theta is just, some scalar value. It's the mean of this thing the log of the posterior distribution. And the derivative is linear, so it's just the sum of the derivatives. And this first part, the derivative of the first part, so I looked up for reference because I knew we were going to need this. I looked up in the video where we computed the MLE for this mean of a Gaussian. And the derivative of this first part from my notes, let's see here, it's 1 over sigma squared times the sum as I goes from 1 to n of xi minus n theta. So these xi's are from our data. Remember, we had our data here. That's our data. And now, so we just need to compute the derivative of the log of p of theta. So theta was distributed normally with mean mu and variance 1. So the probability of a given value theta is, so this is derivative with respect to theta, log, well, let me just write what p of theta is first. P of theta, it's just normal. 1 over the square root of 2 pi, sigma squared is 1, and e to minus 1 over 2, sigma squared is 1, times theta minus mu squared. Mu is the mean now for theta's distribution, and theta is the value that the random variable is taking. So this thing is the derivative of the log of this, the log of the first part, so it's the log of the product is the sum of the logs, log of this is just a constant, so that goes away. So we just get the derivative of, well, let me just write it. So it's minus 1/2 log 2 pi minus 1/2 theta minus mu squared. Derivative of this is 0. And the derivative of this is minus 1/2 times 2. And we're differentiating with respect to theta, so it's 2 times theta minus mu times the derivative of theta minus mu, which is just 1. The 2's cancel, and we get mu minus theta. Okay, so let's plug that back in up here, see what happens. So let's plug that back in. We got the derivative of the first part, and then we got the derivative of the second part. So this equals 1 over sigma squared, sum over x's minus n theta, plus mu minus theta. And that equals, let's see, what can we do with this? So we want to solve for theta. So let's pull together these thetas. This equals, let's do this. Let's do maybe 1 over sigma squared. Let's maybe write it this way. Xi over sigma squared plus mu minus n plus 1 theta. Oh, wait, and I needed a 1 over sigma squared for my n here. n over sigma squared. Okay. So let's see, what do we get here? We can move this over to the 0 side. So this all implies that n over sigma squared plus 1 theta equals this other side. Let's see, did I do that all right? Minus sigma squared minus blah blah blah. Yep, I think that's right. Okay. Mu. Yep, that's all looking good. Okay, and now we want to solve for theta. So all this implies theta is, let's see, it's 1 over sigma squared, sum of the xi's plus mu, divided by n over sigma squared plus 1. So let's multiply through by sigma squared. Maybe we can make this look a little prettier. N plus sigma squared. And so this is our expression for a critical point of this distribution, or of this expression. And to verify that it's a maximum, we need to take a second derivative. So if we take a second derivative of this with respect to theta, we just get, because this is a constant, we just get this minus n over sigma squared plus 1. And this is always negative, so that means that this critical point, which we found, is indeed a maximum. So that's looking good. You know, because sigma squared is always positive, it's a variance. So that's good. And so this implies that theta, let's rewrite this in a slightly different way. We can, so that implies, well, let me just write it here. Theta map, the map estimate, equals this thing, and I'm going to divide, I'm going to write this in as a sum of these two parts. So it's 1 over, well, wait a second. Yeah, okay, that's what I want. Let's actually make this 1 over n times n. We can always do that. So then this is, and this is the sample mean here, well, which I'll write as x bar. So this equals n times, or n divided by n plus sigma squared times x bar, you know, just the sample mean, minus, let's see, minus, is that right? Minus sigma squared over n plus sigma squared mu. Oh, not minus, wait. Where did that minus sign come from? That should be a plus. That was plus, so this is plus. Okay, so now we have our formula, right? I just divided both sides by this n plus sigma squared. So this is our formula for the map. We got the map. This is the maximum a posteriori estimate for theta for the mean of a univariate Gaussian. And this has a very appealing, so you saw, for one thing, that it was not too much harder than computing the MLE. We just had to differentiate with respect to the prior distribution on theta. That's what this p of theta, this is called a prior distribution on theta. So we just had to handle that one extra little part. And this has a very nice interpretation as so it's a convex combination of the sample mean and the prior mean. Prior mean, that was the mean of our prior distribution, and the sample mean. So that's a very nice interpretation.